Hi, welcome everybody to lesson 2.05. We're really starting the last section before we actually take our first test. How remarkable is that? We'll be taking a test towards the end of next week. So this is really interesting. So as you see here, I have a picture and it says fill in the unit circle. Our goal for this class today is really to learn how to do this. So I'm going to demonstrate some things to you, and then I will probably email this to everybody in class, or I'll put a link to it so that you can take this and do it on your own. But we'll work on the procedures and we'll work on all the definitions and kind of the theory behind what we need to think about in order to fill this out. This is going to really help you with the whole degree radian thing, okay? Because especially for all the exact angles, it's going to be one of the ways you see that. In that little table I made you yesterday, you'll see this information again. So it's going to be really beautiful, a lot of really good stuff here. This is something you're going to use all semester once you make it, okay? And so you don't want to just copy it from the internet. You want to make it yourself. You want to think it through. And so we'll talk about that as we go through this lesson and you can start to think it through. Okay, we'll talk to you in a minute. I'm going to set up the next slide. It's right here. So here we are. We are ready to set things up here for today. So the first thing I want to talk to you about is what is a unit circle? A unit circle is a circle of radius 1, okay? Radius 1, and the center is at 0, 0. So whatever we let 1 be, okay, whatever we let 1 be as a item, so I'm going to try and grab a circle here and draw it, and then move it if I can. So there's my circle. It's pretty close to being centered, okay? And so if I were to continue the axes, you see I have a circle here, and this radius here is going to be 1. And that means any radius I draw in this circle is 1. So this is a unit circle, all right? And all you have to do is decide what 1 is, and then you can draw a unit circle. So one of my favorite problems in trigonometry, okay, is stated this way. Okay, so here we go. There's our problem. Good luck. Draw your circle. So I've drawn my circle and my axes. If you do this on graph paper, it's a lot easier. And I've labeled the points, and here's my 1, 0. Now, just by having the circle centered on the origin, I've already got 4 equal subdivisions. So I can sort of imagine what 8 equal subdivisions would look like. It would sort of look like this, right? And I would have an idea that since the whole thing around is 360 degrees, that each of these were 45 degrees all the way around. Okay? I would also have the idea that each of these, instead of being 45, could be what we called pi over 4 radians, right? We could say that as well. So, but what the problem is asking me to do is it's asking me to find the length of this arc. What's the distance around this? Like that. And how can you find an arc in a circle? Well, what we know is since these are 8 equal divisions, I know the circumference of the circle. So the circumference is 2 pi r. the radius is 1, so the circumference is equal to 2 pi. So the length of each of those arcs, since there are 8 of them and they're equal, is going to be 2 pi divided by 8, which is pi over 4. That's interesting. Each arc by itself is equal to pi over 4 as you go all the way around the circle. Now, what this wanted me to do was actually measure the distance from 1, 0 to each subdivision. So the first one is pi over 4. The second one is pi over 4 plus pi over 4. So that one is pi over 2. The third one is going to be 3 pi over 4. The fourth distance is going to be 4 pi over 4, or just pi. So look at that. Can you do the rest of these and get all those distances? Now, what was this angle in radians? Do you remember? What was that angle in radians? Oh my gosh, it was pi over 2 radians. What was this angle in radians? Oh, it was pi over 4 because it's 45 degrees. So we have just found out why this angle is 3 pi over 4, this one's pi, this one's 5 pi over 4. That somehow the measure of these angles is related to the measure of the arc. So let's go on and talk about this a little bit more. What is a radian really? A radian is the ratio of the cut-off arc to the radius of the circle. Okay? So for instance, if we had a circle of radius 2, not 1, and we did this all over again, all right? Now, this angle is pi over 4, all right? Radians. Now, why is it pi over 4 radians? Well, in the same way, the circumference is 2 pi times the radius, which is 4 pi. But if I have 8 equal arcs, that's 4 pi over 8. So the arc length is pi over 2. But the radius is 2. So the ratio of the arc length to the radius is going to give us the angle measurement in radians. And guys, that's what a radian is. And I wanted to tell you this before we kind of headed into the problem. A radian is a ratio of arc length to the radius. Never forget this. This is not in your text, at least not in this way. Okay, now we're going to go back to this unit circle. Actually, my second favorite problem, same problem that does this, they say divide this into 12 equal arcs. So they're all 30-degree arcs now. And they say, what's the measure of the arc in that case? And you're going to essentially do the same process. Find the circumference, but then you'll divide it by 12. So it'll be 2 pi divided by 12, which is pi over 6. So this goes pi over 6, 2 pi over 6, 3 pi over 6 for the arcs. And you measure the arcs all the way around. And you can reduce like 2 pi over 6 is pi over 3. And we get all the familiar ones. Well, what our unit circle is, the original diagram I showed you, it's both of these circles together. So now what we want to do is we want to pick any old angle here and we want to look at a relationship, okay? So I'm just going to go with this angle here. So I have an angle theta here, okay? And since this is actually on an XY coordinate system, this point on the circle is going to have a coordinate XY. Well, now how do I get to that XY? Well, if I knew what that coordinate was, I go out X units and then I go up Y units like that, okay? And that, of course, is going to make a right triangle. Now, once you have this shape, and the hypotenuse of this right triangle is always going to be the radius of the circle, and since this is a unit circle, that hypotenuse is always going to be 1. So now let's write the trig functions, or some of our trig functions, for this triangle. So for instance, the sine of theta's here is going to be the opposite, which is y, over the radius 1. So the sine of theta is just equal to y. And the cosine of theta is going to equal the adjacent, which is x, over the hypotenuse, which is 1, or just x. So the cosine is equal to x. And then finally, let's do our other one. The tangent of theta is going to be the opposite over the adjacent, or y over x, which, just so you know, is the rise over the run. So the tangent of an angle that a line makes with the x-axis is actually its slope. Did you know that? Oh my gosh, now we're connecting all the way back to algebra. So this creates a very interesting situation for us. This tells us that the sine of an angle centered at the origin is always associated with the coordinate on the circle that is y. The cosine of the angle is always associated with the coordinate x. And the hypotenuse is equal to 1 in this case. If you have this situation and then you start to put angle measurements in, so let's put an angle measurement in. Let's start with a special angle, 45 degrees. Okay? Well, if that's 45, this angle up here is 45 because it's a right triangle, and therefore x and y are actually equal to each other, right? Because it's isosceles. But beyond that, because the radius is 1, and I know the hypotenuse is the square root of 2 times the x or the y value, or I could use the Pythagorean theorem. And so in this case, let me use the Pythagorean theorem. I'll go x squared plus y squared equals 1 squared. But x and y are equal, so it's x squared plus x squared equals 1 squared. Because it's a 45, 45, 90, so 2x squared equals 1 squared. So x squared equals 1 divided by 2. And when you take the square root, you get x equals square root of 2 over 2. There's that exact value. So the sine of 45, the x value here, this coordinate, is now actually the square root of 2 over 2. And since y is equal to x in this case, it's square root of 2 over 2. Now, we already talked about this in the last section on special angles. We said the sine of 45 degrees, or the sine of pi over 4, was equal to the square root of 2 over 2. And that's exactly what we get here, except that we note that the sine is associated with the y value and the cosine is associated with the x value. Now, your job is to think about this for the rest of the circle. What if I put a, let's draw it in green here, a 60-degree angle. So now we're looking at a 60-degree angle. Radius is still 1. Okay. Let me erase a little junk here. Whoops. Let me erase a little junk here that's in the way, just so we can see it. Okay, so there's our 60-degree angle, but the hypotenuse is 1. Our triangle is right there. But this would then be a 60, 30, 90. So what's its xy coordinates? Well, the sine of theta will be the y value. The cosine of theta will be the x value. So the sine of 60 degrees is our y value. All right, and that would then be the square root of 3 over 2. The cosine, because we have that from yesterday, and the cosine of 60 degrees is equal to 1/2 right here. And so you could have done it just by your geometry theorem, got your x and y, but that gives you the coordinates of a 60-degree angle. So the question then becomes, what if we get multiples of these angles, right? What if we're down here at 240 degrees, all right, and we make the triangle with the axis? What are the x and y's going to be down here? Now, you might guess something based on this up here, but and some symmetry of the circle, you might be able to guess something, but we can still do it the same way, and we need to talk about one more idea, and that'll really help us with this all the way through, okay? And that idea, so I'm going to keep this here, that is the idea of a reference angle. What is a reference angle? A reference angle is the angle the radius makes with the x-axis. Angle, radius, or line makes with x-axis. So if we had a unit circle of some type, and I'm worried about, remember, all angles are measured from the initial side. So this angle's bigger than 90 degrees, okay? But its reference angle is the angle it makes with the x-axis, okay? If I have another angle right here, all the way like a fourth quadrant, then its reference angle is the angle it makes with the x-axis. Now, where this becomes useful is, suppose you're thinking of some special angles, right? So this is 45 or pi over 4. So this one is 135, 90 plus 45. But its reference angle, the reference angle is 45. It's 180 minus 135, okay? Or the reference angle is pi over 4 in radians, okay? If I had, remember we did, we could do, 13 pi over 6, okay? So 13 pi over 6 is right here. All right, that's 13 pi over 6. What's the reference angle? Well, it's the angle it makes with the x-axis. So we go back. So how far are we away? Well, I didn't mean to say 13 pi over 6. I apologize. 7 pi over 6. That's better. So what's the angle we make with the x-axis? Well, this is pi right here. So you just take 7 pi over 6 minus pi, and the reference angle is pi over 6. Okay? Now, why does all that matter? Well, if you So I explained all this. I got a whole bunch of stuff written here, but I had accidentally hit my voice, so it didn't show up. So I got to redo this slide. Give me just. Okay, let me try this again. I said everything and forgot to place the start, so I had to erase everything, and it looks like it's all erased. Erasing a little more here, and we'll start all over again. Alrighty, here we go. What we have is a unit circle, and we can pick any angle, all right? And so suppose I pick this angle here, which is 5 pi over 6, okay? And so I essentially want to find what is sine of 5 pi over 6 and what is cosine of 5 pi over 6. And now from everything we've done, we know that the sine will be the y value and the cosine will be the x value. So in order to do this, we find the reference angle. So the reference angle is the angle it makes with the x-axis, which is pi over 6. And so if you've made your circle, which you hopefully have done by now, or you have my table that we made in the last lesson, if you have pi over 6, then the x value for pi over 6, remember it makes this right triangle. This is the x, this is the y. And pi over 6 is 30 degrees. This radius is 1. So the y value will be 1/2 because the short leg is half as long as the long leg in a 30, 60, 90. And the x value is square root of 3 times the short leg. So this is the ordered pair that we need to know. And now that we're in the second quadrant, we know that the x value will be negative and the y value is still positive. So the x value is negative square root of 3 over 2, and the y value is 1/2. So therefore, the sine of 5 pi over 6 is 1/2, and the cosine of 5 pi over 6 is negative square root of 3 over 2. And you can do this with any special angle, okay? Any special angle. Now, there's a couple special angles we should at least talk about just briefly, and that's the special angle that'll be at the point 1, 0, all right? The special angle that's at the point 0, 1, negative 1, 0, and 0, negative 1. Well, if you remember, what's the angles there? Either 0 or 2 pi here. And this angle up here is 90 or pi over 2. This angle over at pi is pi or 180. And then this one is 270 or 3 pi over 2. Those are the angles. But since the radius is 1, these points, we already know what they are on the horizontal and vertical axis. We already know what those points are. So if we were trying to do, say, the sine of 270 degrees, and then just for fun, I'll do radians on the cosine. The cosine of 3 pi over 2, we already know what those are. Again, the sine is the y value, so it'll be -1, and the cosine is the x value, so it'll be 0. And that's because we have those ordered pairs. We already know them already. Whereas the other ones, the 30, the 45, and the 60, you have to figure those out from special triangles, which is not too hard at this point. You should be getting well used to that and remember it from geometry. So that's the deal that you have to do. Okay? Whoops. So I want you to look up a chart like we had on the first page. Okay? I want you to look up this. Unit circle values chart blank. If you look that up on the internet, you should get a chart that looks like this. You should get a chart that looks like. If you do that, you should get a chart that looks like this. Fill in the unit circle embedded math. You should be able to go through this and definitely do the first three these triangles right here on your own. All right, we've sort of done them a couple of times, but do those. And then use those in the facts of symmetry and what quadrant you're in to label these things. And then in class tomorrow, I'll show you the table I made last night in yesterday's lesson, and we can use this, and I'll show you how you can always find special angles, and we'll work with that. So that'll probably be in one of our next classes. So also to wrap this up, what have we done? Number one, we have learned about the unit circle and how to use the ratio definitions of the trig functions to find the coordinates on the unit circle. We have also used those coordinates then to then be able to find the values of sine of a theta or cosine of a theta being equal to y or x. And in combination with the idea of reference angles, we can now find exact values of all kinds of expressions with using the unit circle, okay? And for example, you might, a couple of kinds of problems that you might get would look like this. Sorry, this problem's already done. I will explain it again. So a problem type that you might encounter will be something like this, and they're going to say, what is the exact value of the answer? So since these are special angles, 30 degrees, 3 pi over 4, the sine of 30 degrees, I can use my unit circle, or I can know what it is because I've memorized it, is 1/2, which I have there. And the cosine of 3 pi over 4, which has a reference angle of pi over 4 and is in the second quadrant, is going to be negative square root of 2 over 2. So I have to add these two expressions together, which means they need, because they're fractions, they need a common denominator, which they already have. It's 2. So I just need to do 1 plus a negative, or 1 minus the square root of 2 over 2. And this will be the exact value answer. No calculator needed. This is what you can do with trig with special angles. All right. As long as you know special angles, you can do this kind of thing. And we're going to eventually be able to use special angles to actually find exact values of things like the sine of 15 degrees. All right. Half of 30. All right. Or the cosine of 22.5 degrees. All right. So we're going to be able to do half angles and double angles, and we can do weird combinations. Like then we could do like the cosine of 15 degrees plus 60 degrees, like that, which is actually cosine of 75 degrees. So we can start playing a lot of really interesting sort of games to be able to find exact values. And that's all going to come later. We have quite a bit of stuff to do before we do that, but we will do those. Another type of problem that you will see will be this type of problem, in that they will say, okay, suppose you have a point, all right? You know a point on a circle, not the unit circle, any circle. So you know a point. And so let's say that point in this case for this would be like 4, 5, okay? So let's say the point is 4, 5, like that. All right. So what we want to be able to do is we want to be able to find the angle that would go with this particular circle. Okay. So we want to find that angle. So very easily, because I know the point is 4, 5, I know the x value is 4, the y value is 5, and now I want to find the radius. If I want, I can do that by the Pythagorean theorem. 4 squared plus 5 squared equals radius squared. 16 plus 25 equals radius squared. And then that's 41 equals the radius squared. So the square root of 41 is equal to the radius. All right. So this is the square root of 41. And then they're going to ask us something like this. What is the sine of this angle equal to? All right. So for this circle, because this is not a unit circle value, okay, it's just a random point on the circle, the sine of theta is going to be the opposite over the hypotenuse. That's why we use the Pythagorean theorem to find that. So that's going to be 5 over the square root of 41. And once we know that, then we can find theta by taking the inverse sine of 5 over the square root of 41. And there's our answer. In fact, in my old textbook, this is as far as I had to go. I didn't have to give a calculator answer because this is exact. All right? So the inverse sine of a ratio is actually an angle, and then I can find this angle in degrees or radians, depending on the mode my calculator is set up to. Okay? And in general, I would want to do radians, and then degrees I could do if that's what it was asked for. Okay? So anyway, those are kind of a couple types of problems you're going to encounter. So I'm done with this video. Hopefully you'll be okay, and we'll see you next video and next class. Bye-bye.